Right, good morning, good afternoon, good evening, wherever you are. It's a chilly morning in Melbourne and Newcastle and all across Australia. We're glad to have Professor Natalie Thamwattana speak to us in the Matrix Online Seminar today. Just briefly about Natalie, she got a PhD from the University of Wollongong in 2004 and joined the staff there until 2018 when she moved to Newcastle, where she's now a professor in applied mathematics. So Natalie's had a very promising career. She got the J.H. Mitchell Medal in 2014 from the NCM, of which she now is deputy chair. And more generally, she's played numerous leadership roles in Australian applied mathematics, including with the AustMS, AMSI, and the ASC. Natalie's research, which we will hear about today, is in the fields of granular materials, nanofluids, and nanotechnology in general. And she's also been co-director of the Mathematics in Industry Study Group, and I think she'll talk a little bit about that as well today. So it's my pleasure then to introduce Natalie Thamwattana. We do questions in the Matrix Online Seminar via the Q&A button at the bottom of your screen. So if you have a question, please type them in and we'll address them at the end of the talk, and we'll invite you into the conversation so you can ask your question verbally. But please type in your question first using the Q&A function. Over to you, Natalie.
Thank you, Jan. Let me show my screen. All right, so first of all, I guess you can all hear me okay?
Yeah, it's all good.
Okay, cool. So thank you, Jans, and thank you, Matrix, for inviting me to give the seminar today. Just for that, and thank also for the introductions. But this year in February, so I have been bumped up to be a chair of NCMs. So I'm going to be a chair of NCM for the next 2 years. Okay, all right. So I'm talking today about these applications of the reaction-diffusion equations. So I got the invitation from Jan to talk about my collaborative research with industries. So I'm taking that loosely in the sense that I'm talking about the project that I work cross-disciplinaries with people from the fields like in chemistries and also in engineer that they use the mathematics in the application that they also, applied it into the real world problems. So here's the project that I'll be talking about today. So the project that are within the discovery projects, and the project with the discovery project is I'm working with the chemists at the ARC Excellence Center for Electromaterial Science. So that's the DP projects. And then the second part of my talk will be on the project that I work with the geotechnical engineers at UTS, and this is involved the industry partners, and that parts of the linkage projects. And if time permitted, so I'll talk about some problems that we did at the MISGs, and what you expected when you really working within industries. But before I get started, I should mention that I specifically select these two projects to talk about it because one is the discovery project and the other one is the linkage project. And there's a quite these things on the way that I approach the problem. For example, with the discovery project, I feel, like I have the freedoms and to explore a lot of the mathematical ideas, whereas it's a linkage project, you see that I find it's a bit restricted because the project was more particular, and also there's a time constraints as well. As the topics of my talks, all right, so I was trying to talk about those two projects, and I thought, okay, there's an overarching theme of my talk today, which is about using the reaction-diffusion equations in these modelings of the two problems that I'll be presenting today. And I think some of you in the audience know a lot more about the reaction-diffusion equation more than me. So I saw Bronwyn's in the audience as well. But anyway, so I am writing here the reaction-diffusion equations, right? So this is for Rn, right? And so you can derive this reaction-diffusion equation from the fundamental conservation laws, right? And then the important thing to notice here is that these terms here is the diffusion terms, right? Which we assume it's based on the random motions based on fixed law. And we have the reaction terms here, or we can call it the source or the sink terms. Okay, so that basically describe the change in the process, right? So it can be if you're talking about the population dynamics, this can be the birth and the deaths. Okay, if you're talking about the quantity like chemicals concentrations, this can be the chemical reaction terms. So sometimes I write this as f of u, but knowing that u is also a function of x. So when you see my slides next, you see that my reaction term will also explicitly depend on x as well. Now, in that case, the equation will be non-homogeneous. So I will be pretty much doing, so this is I'm writing it in Rn, but you'll see later on that my equation is simplified down because I'm only going to talk about the flow in one dimensions. Okay, all right, so and reaction-diffusion equations have been, used in a lot of applications. And here's just an example where the reaction-diffusion equation has been used in population dynamics. So this I write here some examples of the reaction terms that been used in the population dynamics. In particular, this logistic growth here, that they have particular name for the reaction diffusion equation, which is Fischer KPP equations. I think it had been used in looking at the cell populations, and I think from what I know, Scott McHugh, Matt Simpson, and Bronwyn Hayek's also been looking at particular reaction diffusion equation with these reaction terms are given by the logistic growth. Okay, so that's just an examples about reaction diffusion equations. So what I am doing today is just to adopt these equations and adopt the technique that we use to solve these types of equations and looking for the problems in solar cell technologies. So you can see here is the dye-sensitized solar cells, right? So the dye-sensitized mean that the dye that's sensitive to light. And the reasons that motivate me by looking at this problem, because I used to be at the University of Wollongong, right? And the excellence centers in electromaterial science is the head office is at the Universities of Wollongong, and then I usually go there and have a chat with people. And so they mentioned that they are building, so this was a while ago now, and then they're building this, the SSC dye-sensitized solar cells, right? So the idea is that in the past, when we talk about solar cells, it's a silicon-based solar cells, and silicons, when we use silicon in the PN silicon junction solar cells, silicon itself is so expensive, but it had to be it had to be very purified to be able to make it work properly. So because of the cost in production, so they are looking for alternative solar cell technologies. And the dye-sensitized solar cell was basically introduced in 1991 by Swiss scientists Origels and Gressels. In the papers in their paper in Nature, and I've just looked up that papers. The citation there is about 35,000 now for that paper by Origels and Gressels. So what it is that it is a electrochemicals device, right? So in here, this is a schematic, right? So of these dye-sensitized solar cells. So it comprised 4 major components, okay? So which is the nanoporous semiconductors. And the reason the dye-sensitized solar cells are cheaper than the silicon solar cells because of the use of these nanoporous semiconductors. Because, like, for example, the popular choice is the titanium dioxide. Okay, so that's abundance. Like, you know, titanium dioxide is what you use to, you know, in powders, for example. So this abundance is much cheaper to use it for semiconductors. And coating on top of the so on the surface of these porous semiconductors, you have dyes molecule, right? And the popular choice is the ruthenium dyes. Okay, so so you have nanoporous, right? And on the surface, it's coated with dyes molecules. Okay, and these dyes and nanoporous semiconductors are embedded inside the electrolyte couples, right? And then you have, so it bounds with the glass. Okay, so transparenting conductive oxide. So think of this as a glass. So the suns are shining through from these directions. And on the end, you have the Coulter's electrode, which is commonly used is platinum. So, but they also other studies so to use other materials to make it even cheaper. So in the bracket, what you can see is the titanium dioxide are commonly used, the rutheniums is commonly used for dye, and then the electrolyte couple, there's some other solutions as well. But what I used for the modeling to get this the consents of the models. So we assume that this is the iodide, triiodide solutions, and the Coulter electrodes is platinum. Okay, so so I thought I put this in picture. This picture was used in Matrix for the advertising my talk with me sitting in front of these pictures. So this was a side project because when we was talking to the chemists, they're also talking about, you know, the way that the dyes molecules is, you know, coated on the surface of the nanostructures. And then they're talking about if there's too many of these dyes molecules on the surface, that kind of blocking the transportations of the electron densities, you know, to power the load. So basically, they, you know, there's an optimum numbers of dyes molecules that you want to be on the surface of the titanium dioxide. So and then I have a visiting students from Thailand, and then we have a look at how the bindings of the dye molecule. So this is a ruthenium dyes, right? So you have the rutheniums in the metals, and then you have the nitrogen, and then the carbon atoms, and then you have the hydrogen atoms. So then we're looking at how the binding, you know, the bindings of these ruthenium dyes on the surface of the titanium dioxide, and the orientation. So as the molecules are coming closer to the surface, you know, there is also the preferred orientations, and basically we was able to determine the numbers of dyes per unit areas that, you know, the minimize the interaction energy, and that was done in using the molecular dynamics simulations. But that's just a side story on when we're looking at the interactions of dyes and titanium dioxide. Anyway, so back to the dye-sensitized solar cells here. So really what it is that how this solar cell functions is that when the sun shines, right? So the dye molecules absorb the sunlight, right? And then when the dyes absorb the sunlight, it excites the electron, and then the electrons is injected, okay, into the nanoporous semiconductors, okay, and then it go to power the load, okay, so it go to power the loads, and then the electron get electron holes in the dye get regenerated from the electron within the electrolyte couples, and then as the electron come back to the Coulter electrode, so the electron from the Coulter electrodes fills the electron hole in the electrolyte solutions. Okay, so basically the green arrows is what we prefer to occur, right? So that what is happened, electrons travel through from the nanoporous semiconductor and then go into power the loads, and then it's all come back. And then so that's an ideal world, but in general, not things is quite, you know, nothing is working quite what we want it to be. So in this solar cell, there are also a loss mechanisms that we call the recombinations. So within the recombination, so what it is that instead, which is, you know, in this red arrow here, so instead that the electron, okay, from the dye travel through the nanoporous semiconductors, it fell to the ground state. Right, so it didn't. It excited, but it is in drops. It didn't go further than that. And then the others recombination terms is occurs in this interface here, where instead of travel to power the load, it get regenerated back into the dyes molecule. And the others recombination terms that occurs is at this interface here, where the electrolyte couples, the electron from the dye get regenerated back to the electrolyte couples. So that is a loss mechanism that we need to consider in our models. So how to model these the electron densities within the conduction bands of the dye-sensitized solar cells. So in the very beginning, when the solar cell was introduced, the model was used to look at was based on the solar p-n junction solar cells, which used the Maxwell's equations and some electric potentials. But then in the later state, it was found that the electron transport is not influenced or not much influenced by the electric fields, and so as a result, they say that the diffusions is the important term that govern this electron transport within the dye-sensitized solar cells. So there's some developments of diffusion-based models, okay, by these peoples here. All right, so they start from the linear ODE to the linear PDEs, and then they're further looking at the nonlinear PDCs. So really, what it is this equation here, which is the reaction-diffusion equation. So this is writing in the general forms here. So we have the dye-sensitized solar cell with a thickness D, right? And where 0, and then we have the electron densities N as a function of the position X and time T. So I'm down into the one directions here. Okay, and and when X is equal to 0, so that is at the you know, when it's the glass transparent conductive oxide when the sun is shining to, and this is at the other ends of the solar cells. Okay, so then I have these three terms here, right? So this is the diffusion terms, right? But in here, I say that this is for general purpose here, I write my diffusivity as a function of the electron densities, right? And then I have the general, I have the generation terms. So generation terms, so this is as a function of X. So as the, you know, so we need a function that as the electron densities, as the sun is closer to the sunlight, you know, there's a higher generation, higher source terms, right? And then the profiles is decaying as X is further away from the sunlight. Then we have the recombination terms, and that's just a loss mechanism. So that's why we have the minus signs over here. And there's a lots of research done in terms of determining that what is the function of the diffusivity, the generation functions, and also the recombinations. So I'm writing one here, which is the diffusion terms, okay, is a power law diffusivities, okay, where beta here is the orders of the diffusions, okay, and then note that I use the same orders of the diffusions, okay, in the recombination terms here. Okay, so it's the beta, the same orders of the diffusions as in the recombination terms. But in here, these factors in the recombination terms here is account for a slower recombinations closer to the dark equilibrium densities. Okay, and for the generation functions here, I use the exponential decay function. So you can see that as x equal to 0, we have the high generation function, and as it's further away from x equal to 0 from the sunlight. Okay, so we have a decay terms. Okay, so so this is the reaction diffusions models that we've been playing with. Okay, but I have to say that the generation functions here is based on the Beer-Lambert law, but there's a lot of scope to improve it here because the Beer-Lambert law is actually depend on the wavelengths of the sunlight as well, because you can imagine that during the day as the sun is moved through around the earth, so and then we also have the different wavelengths. Okay, so whereas we try our best to incorporate those wavelengths into our size here and the absorption coefficients here. But in fact, you know, we should somehow try to build in the wavelengths into this these terms here, but that's the next steps. And another importance, I should probably mention that the important points is parameters is this beta here, right? So this beta here, which is our orders of the diffusions. So, and it's also, there's physical meanings of these betas as well, because this beta here is related to the density traps. Okay, so traps in the porous structures. So what it means is that if we have the high values of betas, so that's in the deep traps. Okay, so if there's a deep traps within the porous structures, so which means that the it will be hard for the electron to diffuse. Okay, so to keep that in mind, and we'll come back to that a little bit later on. Okay, and then so now we have these PDE terms. So what we also need to specify is the boundaries and the initial conditions. Okay, so in here, so we use these boundary conditions. Okay, so there's two boundary conditions as x equal to 0, and this is x equal to d, and then we have the initial conditions here. So at these boundary conditions here, okay, and these initial conditions here is based on the Boltzmann approximation for the electron densities for the dark equilibrium given the voltage V. So that basically, you know, what is the dark electron densities when there is no sunlight, given by these terms here. Okay, and also depend on the voltage that we applied it to. Okay, and for this boundary conditions here is meaning there's no flux. Okay, is get into the counter electrode, which is at x equal to d. Okay, then we also have two special cases we can look at. For example, when we have a short circuit condition, so that it's when the voltage is 0. And then when we have the open circuit conditions, when we replace this boundary condition with a Neumann boundary conditions given here. Okay, so together with this, so that we have the boundary values problem, initial boundary values problem that we can solve. But before we solve it, we non-dimensionalized our models, okay, by using these scaling parameters that you can see here, right? And then that's reduced our PDE on the previous slide to this PDEs looking in this form here, where we have this constant mu, nus, size, and omegas are giving as such. And then also our boundary conditions reduced to this these three conditions here. And then in case of the open circuits, right, so we have these two conditions, these three conditions here. Okay, then what we do next is try to solve them, but you can see that this is a nonlinear equation. The first thing that we attempt is, looking at the linear case where we set beta to be 0. Okay, because when beta equal to 0, these terms become 1. These terms become 1. So we had a non-homogeneous but linear PDE that we can solve. And so we can solve it by introducing the change of variables, right? So when beta equal to 0, and then once we introduce the change of variables, we can solve two sub-problem, which is when we solve the ODE in terms of x, and then a PDE that we can use several sub-variable technique to solve these equations. And we obtain the analytical solutions are given like this, which is surprisingly, when we find this, the engineers and the chemists haven't really looking for solving these equations analytically before. They only, put it in the numerical, only to solve it computational way, like numerical results. But in fact, it admits these forms of analytical solutions as such. Okay, and using, so we have these solutions here and the constants A, B's, and CK's. We can find that through our initials and boundary conditions. So we can retain CK's in the in these forms here. Okay. Okay, so this one, I'm looking at the case for the short circuit. Okay, so and then there's another in generals and also in the case of the open circuit, but I'm only presenting one case here when we're looking at the short circuit solutions. Okay, and then we find the parameters here to the literatures and from talking to our collaborators as the SS. Then we can plot. So this is a quick plot that we did in Maple. So what it is here, so that we get is that profiles of the linear case where the solution, where the electron densities rise really quickly. Okay, based on that the generation terms. Okay, the exponential generation terms, and it reached a steady state pretty quickly, as we expect in the linear case of the diffusion models. Okay. What else do I want to say here? So, so this is the profiles of the solution that we get, or I probably should say that when we know the electron densities, then the aim was to be able to determine the performance of the dye-sensitized solar cells. And I'll show you later on how we incorporate, how we use these electron densities, okay, to compute the efficiency of the solar cells, okay, because the electron densities is part of the equation that we use to determine the current and the currents or the powers of the sensitized solar cells. And then we can determine the efficiencies, but I'll show that in the later part of my talk. Okay, and then we also looking, okay, so what happening when we have the nonlinear case, right? And then, so here we try to, for a special case like no diffusion, no recombination, no generation, or only diffusions, right, we can find an analytical solution, but as you can see, it's not quite realistic for a dye-sensitized solar cells. So we also went on with helps of Maureen Edward at the University of Wollongong, looking at the ways that we can, particular function of the N, G of X and R of N, that we can get the analytical solution to Lie symmetries techniques. But then we find that for a particular functions of dn or g of x or r of n, then we can find those analytical solution, but we still have to look into that whether it is realistic or not. So that's further studies on that topics and to look at which of the analytical solution that we get is realistic. But in terms of the general case, so we solve this for another values of beta that's not beta equal to 1, so not equal to 0, sorry. So in here, I'm showing you the profiles when beta is equal to 1 here. So this is a nonlinear case, okay, using the finite different methods. So the profiles is pretty similar for what you see in the linear case, but the scales is a bit different. So, and then this is the comparisons of the profiles of the electron density for various values of betas. So you can see that, because remember betas is correspond to the traps. Okay, so as beta is higher, betas mean that deeper traps in the porous structures. So which mean that electrons is hard to travel. So you see the electron densities is lower when we have the high values of betas. Okay, and then we went on to looking at, okay, so with the properties of the nanoporous structures in here that we're talking about is the titanium dioxide. And we find that these, the porous structures here admit the fractal symmetries. And then we can, there's also a paper in the, that talking about using the diffusions, okay, to fractional diffusion to model the diffusions within a media that has affect fractal symmetries. So then we was thinking that perhaps there is a fractional diffusions that we should build into looking of this transport of the electron densities inside the dye-sensitized solar cells. So our work was based on Bruce Henry's works and Werns. So they proposed that there's a fractional reaction diffusion equations of these forms here. Okay, now the important parameters here is gamma. Okay, so gamma is the powers of the mean square displacement. So what is this also mean that gammas here is depend on the porosities of the medias that we're looking at. So it means that if low gammas is correspondent to a longer path. Okay, so which means that when that's occur when we have a low porosities. So there's different definitions of the derivative that exist in the literature. Some use the Riemann-Renovier's definitions, but what we use is we use the Caputo derivative to simplify our equation 1, right? So when we use that, these terms here, okay, disappears, and what we got is the fractional diffusions given in here, where our functions, the reaction terms is what you've seen before, which is generation term, and the recombination terms. So I'm just looking in the case where here my beta is equal to 0. Okay, so and you can see that when gamma is equal to 1, these terms, all this equation here is correspond to what I have previously for the linear case. Okay, so I also say here that gamma, when small gammas, it means low diffusions. Okay, so we should mean that it's a longer path for the electron to travel. So that's important parameters here. And the boundary conditions and the initial condition is the same as what you've seen before. Okay, and then we plot. We tried to solve analytically, but wasn't successful because of our reaction terms. So we went on to do the numerical solutions, and we find that as we expected, the low values of gamma, so it's hard for the diffusions. Okay, so it's a low diffusion, so you can see that in here. But the electron densities is highest where when it reached. Okay, so you can see the electron densities is higher for the lower gamma, but it's hard. the diffusions is slower to reach the steady state. Okay, then here, okay, so, and then I want to say, probably, I know I'm a bit low on times, but so, okay. So as I said before, now we get the electron densities, right? And the purpose of it is just to use the electron densities in the diode equation so that we can compute the current. And then when we compute the currents, we can get the powers, and then we can determine the efficiencies of the dye-sensitized solar cells. And this is our diode equations, okay, where the JSC is a short circuit current densities here. This is where we use the electron densities here. Okay, and through that we want to maximize the power's output, because this is what we need here to find the efficiency, right? So efficiency is the maximum power's output divided by the powers of the incidence slice. So through this relationship here, we first find the maximum voltage. Okay, once we find the maximum voltage, and then we can find the maximum currents, and then we can then find the maximum powers. Okay, and then using that constant PI, which I probably given in the previous slides already, we can find the efficiency of these dye-sensitized solar cells for the different values of gammas. So noting that when gammas is equal to 1, that is in the linear case. So you can see here as the low values of gammas, you have the low efficiency, and when you have the high values of gammas, so that mean you have a highest efficiency here. And then I pops in gamma equal to 0.612, and that is a values of gammas that corresponding to the porosities about 0.4, which is what is used for the titanium dioxide. Okay. So that is one part of my talks. Okay, so that is the use of reaction diffusions in with the in the projects that looking at the solar cells. So you can see that I was able to extend a little bit further into looking at the fractional, so and then we looking at least symmetry techniques and others. We was able to explore the mathematics further into looking into modeling the problems. So the next part of my talks is the project that I work with industry. So basically I was told that this is what we wanted to do, and then we'll have to come up with the solution for that. So in this part, we're talking about models of the flow underground flows. Okay, so what they have is that they have the psi, right? So that is so the underground waters that passing through this size is acid. Right, so what they're trying to do is trying to create barrier, right? So that as the acid water flow through, this barrier neutralize the acid waters, and then before it releasing water to the water sources like rivers and things like that. So they basically try to treat the water before it get released to water's main sources. And what we do in here is that these reactive barriers is that we use is an alkaline materials, because the water that comes through is acid, right? So we need to have like an alkaline with base materials to neutralize the waters. So in the past, the engineers that I work with, they use the crushed recycled concrete, but it's found that because it's from the concretes are coming from the different sources, and so it had to control the property, the site distributions of that concrete. So in the project that I'm currently work with, they're using this limestone, the calcitic limestone, and that come from the factories in Mossville near Wollongong, and then because it come from the factory, so they can control the size of the materials and the pores, and so that you can control the site distribution as it's being used in the construction site. But what happens is that, so we want to know the performance of these reactive barriers, whether, when we can replace it, right? Because what happened as the waters flow through that, the reactive barriers, it starts to get clogging over time. It's clogged, right? And the clogging occurs due to the physical clogging, chemical clogging, and biological clogging. Okay, so because what is the acid that has some minerals that come through, so there's some chemical reaction within the size, and then it starts to aggregate. They start to have the deposit of minerals within the barrier itself, and then because of these waters are what's it called, acid, right? And then there are also some bacteria that living in this reactive barrier as well. And as you can see that the bacteria start to grow, and there's some byproducts, and the growth of bacteria that also, increase the cloggings of the of this PRB, the reactive site. So by looking at these cloggings and how the cloggings, occurs, or model this clogging, so we can see that when we should start to replace, or the performance of the reactive barrier, and when we can replace these reactive barriers. So these are some of the pilot scale site that they installs in Shoalhaven. So this was the when they used the concrete crush up, right? But in the project that I'm working with, we looking at the limestone aggregate. Okay, so what you can see is that we're looking at the column experiments here, right? And so ABCs is basically over time. So that's for like 7 days, 130 days, and about 250 days. So as you can see, the water are flowing in. Okay, the first columns, okay, is where we only have the chemical clogging. The second columns is when we have the chemical and biological clogging, and you can see that over time, okay, the clogging. So in the top pictures here, this is when we haven't introduced the bacteria yet, because we have to introduce bacteria when the acid is at the pH is about 2 or 3. So at the beginning, as the water flow through, the acids are not quite right. So in this picture here, the second columns is already been introduced by the bacteria, is already been introduced in that column. And you can see that comparing to the first and the second column, the two with the bacteria are a bit more clogging. And you can see also the aluminium precipitate, which is in this white. And the orange colors is the iron precipitate. So you can, and then over time, it's very clogged in both columns. Okay, so so how we model so what we're doing is that we're looking at the porosity first, okay, because the porosity is reduced by the clogging due to the biomass, okay, of the bacteria, and also by the mineral precipitate that due to the chemical reactions. So, and then we say that the porosities over time is equal to the initial porosities, subtract the reductions, okay, of the porosity that occurs within the biomass and the chemical precipitate. So note that we use these models here to represent the growth of the bacteria. So this is based on the monokinetics for microbial growth. Okay, and so we can then get the porosities, okay, which is given by these equations here. Now, we're looking then at the equation to look at the transient flows to the porous media. Okay, so so I write here as is a 3D models, but later on you can see that I reduce this down to 1D models because I assume there's no cross flow, and you can see from the experiment the flows is in one directions. Okay, so now I'm looking at H here is the hydraulic head. Okay. And so you can see that that's just basically, the amounts of water that is flowed through these porous medias over time, right? So what interesting things when you work with the people from this different disciplines is that they interpret the terms differently. So K here, right, the K sub XX or KYY, okay, that's that there is the hydraulic conductivities, right? And when I talk to people in soils, they sometimes call the hydraulic conductivities a permeabilities, but basically, in principle, they're different because the permeabilities is the properties of the mediums alone, right? But the hydraulic conductivities is the properties of the mediums and also the properties of the fluid. And then they have this relationship. But when we work with people in soil, they say that because of the viscosities of, there's not much of the change of temperature over time. So these terms here are very small, so they can use the word hydraulic conductivity and permeability interchangeably. But anyway, so here there's a relationship between the permeabilities and the conductivity, which we need because when we use the Kosinski-Kármán's equation that link the permeability with the porosities, and this is what we got here. Okay, so and if you know this Kosinski-Kármán's equation, you know that this M here is specific surface of the particle, but it's a very complicated definitions that's given, and lots of engineers just assuming this to be a constant. But anyway, so with that and the N's, which is the porosities that we derived it previously, and we can obtain these terms here for the normalized. So that's normalized mean K, the hydraulic conductivity divided by K naught, which is the initial hydraulic conductivities, and we get these relationships here. Okay, and so the constants in front just disappear because we normalize them, and we use the N, okay, which is what we had in the previous slide, which is the porosities of the columns that due to the cloggings of the minerals and also the biological cloggings. So we have that, and then as I said, my flows, I'm only looking at 1D. Okay, so I'm nearly done here. Okay, so we're looking at the flows in 1D, right? So the other terms, X, Y's, X, Y, Y's, and Z's disappear. So I reduce to these equations, right? And we know that K is a function of times, right? So therefore, I got this equation here, which is similar to the reaction-diffusion equation, but because of these terms here. But nevertheless, I can use the separation of variable to solve for general solutions. Okay, but the term J of T is quite a bit complicated. But nevertheless, when we're looking at the several separables of separation of variables, we are able to integrate this, okay, analytically, and it's given by these formulas here. And then we can determine the constant lambda, C1 and C2 by using the initial and boundary conditions, but I'm skipping that. And then we can show, we can plot our models with the experimental results, okay, the fielded object here, the fielded object lines is our models, and the experiment one is the one that's the objects is unfilled. Okay, so over times, okay, so it works well, except that when it's closer to the when the times is going really long times, it means that the models does not really work well, and that when they as at around in this here where the the bacteria growth is starting to die out. Okay, but in our models, we didn't build that into the model when we're looking at the death of the bacteria. So that's a result why our models here are not matching well with the experimental results. Nevertheless, it's give quite a good agreement. Okay, and that was, you know, and then so now the research that I'm working with them is to use these terms here, right, that we developed here with the biologicals and chemical cloggings. Okay, so chemical and biological clogging, and looking at the consolidation theories and how, you know, the compact the soils would be when there's, you know, there's a clogging occurs. All right, and and also the work that we did in this project is now looking. They introduced this permeable reactive barriers in the Hunter Valleys, in the construction site somewhere in the Hunter Valley, by using this limestone aggregates based on the models that, and the experiment that they've developed. Okay, I know that I'm running out of time, so I'll only talk a bit briefly here. Is that okay? So so in the 2020 to 22, we have these MISGs at the University of Newcastle, and these are the project that we're looking at. But it's quite interesting to see, you know, working with industries. So for example, I have no ideas at all. So I was sitting with the group of aerodynamics and controls of the next generation electric rotorcraft, and I have no ideas at all how to you know, model that equations. But you know, we're working with other peoples, and then I learned that we don't need to be aerodynamics engineers to be able to work into problems. And it's funny that when we talk to the industries, the industry was expecting that the equations will be solved by engineer. They didn't realize that it's actually, you know, the fundamental ideas that, you know, to look into solving this problem, you know, they need mathematicians. So they was very surprised that we were able to give them solution that they was expecting to receive from the engineers. Yeah, so having said that, is really interesting in working in a lot of this project, because you're learning quite a bit of new idea, and also you get to use, you know, my background is in granular materials, so what I was able to contribute it there, but people with a different backgrounds, like, you know, in computational approach, for example, say, you know, they model this with the like finite difference method. So it's interesting to see where, you know, the contributions are coming from people with the various background to solve the problems. Okay, and I should probably say that this is going to be at Monash in the next 3 years. Okay, and Mark Flex is the director. So if you have any questions, so Mark said he's happy to be in contact. Okay, and just to wrap it up, so then take-home messages is that a lot of problems, especially in industries, surprisingly require mathematics and statistics to solve them. And sometimes this industry people doesn't really know that, you know, they need maths and a mathematician to solve the problems. So they expect, you know, there's going to be engineers, but yeah, they were surprised that, you know, the mathematics can do a lot more for them. My other advice is that, you know, it's easier to start with some things simple before we start to add in the complexities of the models, because that's how, you know, you can build, start it with something simple and then you can add it up, and then you can check the models as well. So my experience is that cross-disciplinaries take an effort, because I need to learn, like, for example, I need to learn a bit of chemistries. I need to learn you know, the words and the terminology that they use in geotechnical engineers, which is different than what I've done in mathematics. But, you know, it needs a lot of effort, but, you know, it's rewarding when it's actually being used, especially in the project that I work with the geotechnical engineers. And for those of whom are thinking to work with the industry, so the good place to start is attending MISGs or supervising students to doing MC internships. So 2 of my students are at, you know, taking internship program. The supervisor was my colleagues here, Mike Mellon. But having said that, you can see that the student that come out from internship program does grow, and they does, you know, become attractive as the candidate for later on to work in the industries. So I will just stop it here. I know that I went quite long. I'm sorry about that. So I'm thanking these people here for their help with the projects. Okay, and also the ARC and my colleague Mike Mellons, who are the co-directors. Thank you, and sorry for taking too long.
Thanks, Natalie. No, that's all right. So let me applause on behalf of everyone who's attending. Thanks so much for an interesting talk. So you can submit questions through the Q&A, and then we'll invite you in as a panelist. So I see there's questions by Dan McKinley. Dan will invite you in, and as soon as you're in, you can open your mic and video and ask your question.
Right. Hello. Thanks. That was great, Natalie. Yeah, I had a bunch of questions on a similar theme, which were about how you deal with parameter estimation and model estimation and noise in these models. So I guess I might just ask all those at once. How do you deal with all these three factors, especially in the first? Well, they all look like very noisy PDEs, right? So yeah.
Yes. There is a lots of parameters. You can see there's a lots of parameters involved. Yes, and the parameter itself depends on the materials that we use in the models, and different materials given different parameters. So, but I probably should go back into, sorry, that's when I normalize them. Okay, so just go waste here. So when we normalize them, so we have this parameter, nu, mu, size, and omega here that we're working with. And then it's the normalized parameters here. But having said that, we haven't really done the parameter sensitivity analysis to look into really which one of it is, playing the important roles in the behavior. And yes, it's very noisy PDE, and but I haven't really done much in terms of looking at the stochastics models of this PDE. So it's just, there's a lot of avenues to go ahead from now on, but I haven't really taken that road yet.
Can I ask a quick follow-up question? Because I had the same when listening to your talk. So do other people include stochastic terms in the PDEs?
No, not that I know of. So this works usually, in the chemistry journals, right? And when they're looking at it, they just propose the PDE, and then they go on and then solve it numerically.
Okay.
So, and then there's this, the diffusion-based approach has only recently developed, and it has not much, there's not many models that been, looking into further develops it to include the stochastics diffusion process.
Okay, let's go to the next question. Thanks again, Dan. So again, if you have a question, please submit through Q&A, and then we can invite you in. So the next question is by Scott McHugh. Scott will invite you in, and you can ask your question in person. Yeah,
I saw what he wrote.
Natalie?
Yes.
Can you see me?
Yes, I can see you and I can hear you.
I sort of lost the connection then for a moment. So Natalie, you mentioned you were looking for some exact solutions using Lie symmetry analysis of some of your reaction-diffusion equations.
Yes.
And then you mentioned some fractional versions of those reaction-diffusion equations. Have you tried to use Lie symmetry analysis to find exact solutions to the fractional versions of your models? And, does that even work? Do you know anything about that, for example?
I don't know. Maybe I should ask and invite Bronwyn to help me here, because I don't know that the Lie symmetry techniques is working with the fractional models.
Well, that's part of the question, I guess, whether you know about that or...
No, I don't know. And then I was also, this is in the size topic that I work. So I have this integral partial differential equations, and then we should like involve the non-local terms. And I talked to Phil as well, and Phil said, even the partial, integral partial differential equation with the non-local terms, Lie symmetries is still not quite there yet. So
something for the future.
So something for the future. So I haven't really, explore whether there's a Lie symmetry techniques that for the fractional diffusion equations.
Okay, good. I see Brendan's there. She might be saying something.
No, I just dropped out a little bit too as I connected in, but I think I heard Natalie say that Phil said symmetries analysis isn't quite there yet for fractional PDEs.
No, for the other one, for the non-locals,
for the non-local one.
Non-local, when you had the partial integral partial differential equation with the non-local terms. So,
but fractional derivatives can be written as integrals, can't they? So
the fractional derivative that the way that we use it, we write it as a series. Series summations, and that's how we put it in the numerical method. So it might be the way that but we haven't tried yet.
Okay. Well,
but I don't know much about it.
Good.
And the Lie symmetry that we've done here, so I need with the help of Maureen from Wollongong.
I'll have to try to leave this, or maybe I can get booted. Can I?
Yeah. Thanks, Scott, for the question.
You can boot me.
We'll move on to the next one by Matej Shaspari. We'll invite you in.
So I see the questions.
So Matej, I'm not sure how to pronounce your name. You're in now. You should be able to open your mic and video.
Hello. Good morning. Thanks for the talk. Very interesting. So my question is the function spaces that are suitable for these solutions of PDEs. And the second one is when you try to solve the equation numerically, how do you make sure, that numeric solution, approximates and, it's in the same space as well.
Okay. So you mean this dn g of x at r of n, how we determine this? Lots of.
I think the question is if you solve for n in this equation, how do you make sure it remains the appropriate properties, that it stays inside a certain function space? Okay,
so basically we compare our results with the results in the literatures. Right, so I didn't have a slice where I did when we solve it numerically, and then we kind of using a different techniques as well. Like we're using finite difference, we're using the other finite elements, and we kind of compare that our solutions behave similarly, and then we also compare our results with the numerical results that in the other papers. Then we kind of say, okay, this is giving us the same kind of behavior, but we did not go into details in terms of proving anything more rigid. Does that kind of answer your questions?
Okay. Yeah. Thanks a lot.
Yeah.
Okay. Thanks, Matej, for the question. So next question is from Vishnu. Vishnu will invite you in.
Vishnu, you are working with me on this.
Not supposed to ask questions.
No, it's all right. Vishnu has helped me a lot with this in PhD students and with this numerical methods.
You should be able to open your mic and video, Vishnu.
Okay. Yeah. Now I think you can hear. You can hear me.
I can hear you, Vishnu.
Just a question about this gamma, the fractional
Yes.
parameter gamma. How do we estimate that?
Yes, so gamma, I probably didn't mention that quite clearly. This gamma here is related to the porosity of the medias.
Yeah.
So there's a relationship, so I didn't mention here, but the relationship between this gamma here and the porosities, right? So you can see that when the porosities is quite high, so we talk, and then so it's a longer path length for the electron to travel, and as a result, this means that it's slow to diffuse. So, and the gamma that was, so we find that, like for example, in the titanium dioxide, the porosities was about 0.4. And so that's somehow correspond to this gamma is about 0.612. And then we can show that that's the case. But in the literatures and then the chemists, people saying that high porosities is not good, but also low porosities is also not good. Yeah. So there's an optimum values of the porosities that making this this sensitized solar cell to work well. And some literatures found that it's about 0.4. Okay, but having said that, if you notice it here, I didn't mention it here, this is very low. The efficiency of this dye-sensitized solar cell with the parameters that we're looking at here is very low, and it's still a very active area of research to develop a nanoporous semiconductors, new dyes molecule, new electrolytes, and also hold that structures to improve these efficiencies. And I have to say that the models are hard to catch up, because now they develop all kinds of different types of organic solar cells that furthers than what we done here for the dye-sensitized solar cells.
Yeah, thank you, Natalie, and thank you also for the interesting talk. Yeah, thank you.
Thank you.
Right, thanks, Vishnu. And that brings us to the end of the questions. It's a good time to wrap up. So thanks again, Natalie, and thanks everyone for attending. And I hope to see you at our next seminar next month.
Thank you.
Okay. Okay. Goodbye, everyone. Bye-bye.
Bye.